This video is going to focus on indicators of acidity or alkalinity. So, students often come across indicators in the GCSE course, and they come in two main categories. Simple indicators, which tell you whether something is acidic or alkali in nature, and then more advanced indicators, which not only tell you whether something is acidic or alkali, but also the extent to which it is a strong or weak acidic or alkali solution. The first three indicators I'm going to talk about today are simple indicators, which tell you if something is an acidic or an alkali solution. The first indicator is called litmus, or litmus paper. Most students come across litmus paper rather than the litmus solution itself at GCSE level. So litmus paper is a really nice simple indicator which gives you a nice visual indication that a solution is acidic or alkali. For example, if I had a beaker containing 1 mole per litre hydrochloric acid or 1 mole per litre decimeter cubed sodium hydroxide, looking at them, I'd have no way of distinguishing between them. They're both colourless, odourless liquids. So I'd take my pieces of litmus paper, dip them into the solutions and watch for the corresponding colour changes. So to test the acidic hydrochloric acid solution, I would take a piece of blue litmus paper, dip it into or submerge it into the acid, and I'd find that the end which was submerged in the acid would turn from blue to red in the acidic conditions, indicating that it was an acid. Vice versa, if I wanted to test the alkali solution, the sodium hydroxide solution, I would take some red litmus paper and dip it into the solution, and the end which was submerged in the alkali solution would turn blue. So very basically, blue litmus paper turns red in acidic conditions, and red litmus paper turns blue in alkali conditions. The second indicator I want to talk about is methyl orange. So methyl orange is, here's my dropping pipette, and you can see that the original colour of methyl orange is that it's an orange solution. But I've got 3 different conical flasks with 3 different environments. I've got a 1 mole per decimeter cubed solution of hydrochloric acid, some water, and a 1 mole per decimeter cubed solution of sodium hydroxide, which is an alkali. You can see that when the methyl orange was put into neutral solution, it stayed orange. When the methyl orange was placed into the acidic conditions, it has turned deep red. And when the methyl orange was placed into the alkali conditions, it seems to have turned slightly more yellow. So methyl orange changes from orange to red in acidic conditions, and it changes from orange to yellow in alkali conditions. So the function of methyl orange is generally to test for the presence of acids, because you get that really vibrant red colour change. So it gets used in titrations because it gives a nice permanent clear, and by clear I mean very obvious, permanent colour change, and a sudden colour change in a very particular pH range. So in titrations, you'd be adding an acid into an alkali, so an acid from the burette into an alkali in the conical flask. And as soon as the solution became even slightly acidic and you had added enough acid to neutralise the alkali, then the entire solution with methyl orange would go from orange to red in the conical flask, indicating that change. So that would be a use for methyl orange. The other indicator which gets used a lot in titrations is called phenolphthalein. Quite a hard one to spell, with PHTH in the middle. But you can notice again from my dropping pipette that phenolphthalein is a colourless solution initially. And again, I've got my 3 conditions: my acidic conical flask, my water conical flask, and which is neutral, and my alkali conical flask with sodium hydroxide solution. And you can see that upon addition to the acidic and neutral solutions, the phenolphthalein has remained colourless. But upon addition to the alkali conditions, the phenolphthalein has changed to a vibrant, bright pink colour. And again, in titrations, if I were to be titrating an alkali into an acidic solution, I'd add some phenolphthalein to my acidic solution in the conical flask, slowly add my alkali solution from the burette, and as soon as the last drop from the burette turned my acidic solution in the conical flask even slightly alkali in nature, then there'd be a sudden change to pink, and I'd know that I'd reached that endpoint. So phenolphthalein turns from colourless to pink in alkali conditions. Never ever say that phenolphthalein turns from clear to pink. Clear does not mean colourless. Clear means transparent, essentially, or translucent. So don't say clear, you mean colourless. Finally, universal indicators. Universal indicator is very useful because it gives us more information. Not only does it tell us whether something is acidic or alkali, but it gives us some indication of the strength of the acid or alkali, and therefore the relative concentration of hydrogen ions. And that's through its colour range. So universal indicator turns red in highly acidic conditions, in strong acidic conditions. And that could be a pH range of 1 to 3. If universal indicator is added to a solution and it turns more orange in colour, that might be indicative of a pH of approximately 5 or 5.5. If the universal indicator turns yellow in the solution, it's an indication that it's just a very weakly acidic solution of pH 6. And if it turns a nearly green, nearly bright green with a slight faded green colour, it might be incredibly close to pH 7, maybe pH 6.5, 6.6, something like that. Your vibrant green colour is an indicator of neutrality, pH 7. A dark green colour might indicate you're moving away from neutrality towards alkalinity, and so pH 8. And then varying degrees of light to dark blue would be pH 9 for the lighter blues, and deeper blues would be pH 10 or 11. And then highly alkali conditions, highly alkali situations, you get a purple colour, violet or purple colour in your universal indicator, which is an indication of pH 13 to 14. So as you can see, universal indicator, useful in that it gives you this greater depth of information, but again, limited in the fact that some of these ranges are quite broad for the same colour. So red could be quite a large range of possible pHs and therefore have actually quite large differences in hydrogen ion concentration relative to those numbers. So it does have some limitations. I hope that was useful in recognising the 4 key indicators covered.